Hello, in this video we begin our unit on electrochemistry. Electrochemistry is the branch of chemistry that studies the interchange of chemical and electrical energy. And this unit is important because in many ways it brings together what we've been studying for the past several units about equilibrium and spontaneity and useful work. In this unit we're going to study two important processes. The first is how we generate an electrical current from a spontaneous redox reaction. That's important because an electric current can do useful work. The device that performs this is called a galvanic or voltaic cell, and much of what we'll talk about is how we describe voltaic cells. The second important process is when we use an external electric current to cause a chemical reaction that is non-spontaneous to occur. That process is known as electrolysis, and the device that performs this is called an electrolytic cell. Every time you plug a device in to recharge it, you are essentially doing this process. So let's begin with our first section, balancing oxidation-reduction equations. Now you may say to me, but I know how to balance equations already. Well, it turns out that these cells, both the voltaic cells and the electrolytic cells, are very often based on oxidation-reduction reactions that are very, very complicated and would be difficult to balance by standard methods. So scientists developed a technique called the half reaction method that is extremely useful and extremely powerful. I love it because it always works. No matter how complicated your reaction is, if you apply this method correctly, you will get it to balance. And it essentially goes like this. The first thing you do is to look at your overall reaction and split it up into two half reactions, one of which describes the oxidation part and the other of which describes the reduction part. You will recall that every redox reaction involves an oxidation, in which one element loses electrons, and a reduction, in which another element gains electrons. So we're going to look at these two processes separately. We will then balance each half reaction separately using free electrons in order to get it to balance. In an oxidation process, which involves loss of electrons, the free electrons will be on the product side, whereas in a reduction half reaction that involves gain of electrons, the free electrons will be on the reactant side. Once we have balanced each half reaction separately, then we will add the two balanced half reactions together, canceling electrons, as well as any other species that appear on both the product and reactant side, in order to obtain the overall equation. So, let's start with a very simple example. If I place a strip of zinc metal in a solution of aluminum 3 cations, I will form aluminum metal and zinc 2 plus cations. So you may look at that and say, so what's the problem? It's balanced. I have one aluminum on each side and one zinc on each side. But if you look closely, you will see that what's not balanced are the charges. So no, this is not a balanced redox reaction. In fact, if I were to write this not as a net ionic equation, but instead include, let's say, chloride anions to neutralize the charges, I would see an equation that looks like this, and immediately, of course, you see that it's not balanced. And you would say, okay, this is pretty trivial. Chlorine comes in groups of 2 on the product side, so I'll put a 3 here. It comes in groups of 3 on the reactant side, so I'll put a 2 here, and then balance the zinc and aluminum like that. Okay? Well, yes, that's pretty straightforward, but what you actually did here was to look at half reactions. So let's consider the oxidation of zinc and the reduction of aluminum separately. Aluminum 3 plus ions undergo a 3 electron reduction to form aluminum metal, and the zinc metal atoms undergo a 2 electron oxidation in order to form zinc 2 plus cations. In order to add these two half reactions together and to balance electrons, because a fundamental principle in this method is the total number of electrons lost in the reduction step, lost in the oxidation step, must be gained by the reduction step. And as you can see in this case, 3 electrons on the reactant side do not cancel 2 electrons on the product side. In order to get electrons to cancel, I must multiply the reduction half reaction by a coefficient of 2, and I must multiply the oxidation half reaction by a coefficient of 3. When I bring these together now, and I'm going to rewrite these as 2 aluminums cations plus 6 electrons form 2 aluminum atoms, and 3 zinc atoms form 3 zinc 2 cations plus 6 electrons. Now when I add these half reactions together, the 6 electrons on the reactant side cancel the 6 electrons on the product side, and I get 2 aluminum 3 plus 3 zinc form 2 aluminum plus 3 zinc 2 plus, which we see is essentially the same reaction we had above. Okay, so here are the steps in the half reaction method. And again, if you follow these steps, you will never go wrong. Step number 1, assign oxidation numbers to every element on each side of the equation, and based on changes in oxidation numbers, identify which element is being oxidized and which is being reduced. If you need to go back and review assigning oxidation numbers, we will certainly go over that. Step number 2, you'll write separate equations, which are the half reactions for the oxidation-reduction steps. And then you will balance each half reaction separately. Begin by balancing all elements other than hydrogen and oxygen, simply by using whatever coefficients you need. Balance oxygen by adding as many water molecules as you need to either side. Because these reactions occur in aqueous solution, you can use as many H2O molecules on the reactant or product side as you need in order to balance oxygen. Balance hydrogen by adding hydrogen ions, H+. We'll begin by considering reactions that occur in under acidic medium, meaning that there is an excess of hydrogen ions, so simply add as many H+ ions to either the reactant or product side as you need to balance hydrogen. At this point, you will recognize that the charge is not balanced, so finally, balance the charge using electrons. Now notice that the number of electrons gained or lost in the half reaction must be equal to the change in oxidation number. And that makes perfect sense, and we'll see some examples of that in a second. Once you've balanced the oxidation and half reduction reactions separately, then you simply multiply one or both by whatever integer you need to, so that the total number of electrons lost in the oxidation is equal to the total number of electrons gained in the reduction. And we saw that in the previous example. And then finally, add the two half reactions together, cancel anything that appears on both sides of the arrow, and then check to make sure that your elements are balanced and that your charge is balanced. Let's do some examples. So here's a reaction in which hydrogen peroxide reacts with nitrogen monoxide to form water and the nitrate anion. I'll begin by assigning oxidation numbers. Hydrogen is +1, oxygen in peroxide is -1, in nitrogen monoxide, nitrogen is +2, oxygen is -2, hydrogen +1, oxygen -2, and in nitrate, oxygen is -2 and nitrogen is +5. So we can clearly see that oxygen is being oxidized, oxygen is being reduced, it's going from -1 to -2, and nitrogen is being oxidized, it's going from +2 to +5. So let's begin by balancing the oxidation half reaction first. We've got NO forming NO3-. I will balance oxygen by putting 2 water molecules on the reactant side. I will balance hydrogen, sorry, that's 2 water molecules there. I will balance hydrogen by putting 4 hydrogen ions on the product side. And in order to balance the charge, to have an overall charge of 0 on both sides, I will add 3 electrons to the product side. So there is my balanced half reaction for the oxidation of NO to NO3-. For the reduction, hydrogen peroxide is being reduced to water. I will balance the oxygens by putting a 2 before H2O on the product side. I will balance the hydrogens by adding 2 hydrogen ions to the reactant side. And then I'll balance charge by putting 2 electrons on the reactant side. Notice that in your oxidation half reaction, electrons must always be on the product side, and that in your reduction half reaction, electrons must always be on the reactant side. Notice also that the number of electrons gained or lost must equal the change in oxidation number. Nitrogen is being oxidized from +2 to +5. An increase in oxidation number of 3 corresponds to a 3-electron oxidation, which we clearly see in the loss of 3 electrons in the oxidation half reaction. Correspondingly, oxygen is being reduced from -1 to -2 in both products. That is a decrease in oxidation number of 1, but because there are 2 oxygens in hydrogen peroxide, that's a total decrease in oxidation number of -2. consistent with a gain of 2 electrons. It all makes sense. So, can we add these two half reactions together now? No, we can't, because 3 electrons lost in the oxidation do not cancel 2 electrons gained in the reduction. The least common multiple of 2 and 3 is 6. So in order to have a total of 6 electrons lost and gained, I must multiply the oxidation half reaction by 2, and I must multiply the reduction half reaction by 3. Now, please do not try to take any shortcuts here. You will confuse yourself. Write the equations out again with your coefficients being distributed. So that gives me now, for my modified oxidation half reaction, 2NO plus 4H2O reacting to form 2 nitrates plus 8 hydrogen ions plus 6 electrons. And for my modified reduction half reaction, in which I've multiplied the coefficients by 3, that gives me 6 hydrogen ions plus 3 hydrogen peroxide molecules plus 6 electrons, forming 6 water molecules. Now I can add these two half reactions together and cancel what appears on both sides. So what does appear on both sides? Well, obviously your electrons cancel. If they didn't, you did something wrong. I've got 6 hydrogen ions on the reactant side and 8 on the product side, so these all go away, and this becomes a 2. I've got 6 water molecules on the product side, 4 on the reactant side, so these all go away, and this becomes a 2 as well. So now when I add my two half reactions together, I have 3 hydrogen peroxide molecules reacting with 2 nitrogen monoxide molecules to form 2 water molecules plus 2 hydrogen ions left plus 2 nitrate anions. And if you pause the video and look very carefully, you will check and see that not only do atoms balance, but charge balances as well. That is an example of using the half reaction method under acidic conditions. Let's do one more example. So here we have sulfite anions, SO3 2-, reacting with permanganate anions, MnO4-, to form sulfate anions, SO4 2-, and manganese 2 cations. If I assign oxidation numbers, oxygen has -2 in everything. That means sulfur and sulfite must have an oxidation number of +4, manganese and permanganate +7, sulfur and sulfate +6, and manganese 2 and manganese 2, of course, +2. So we see that sulfur is being oxidized from +4 to +6. Manganese is being reduced from +7 to +2. So I'll write out my oxidation and reduction half reactions and balance them separately. In the oxidation half reaction, sulfite is oxidized to sulfate. To balance oxygen, I will put 1 water molecule on the reactant side. To balance hydrogens, I'll put 2 hydrogen ions on the product side. And then to balance charge, I will put 2 electrons on the product side. Once again, in an oxidation, which is a loss of electrons, the electrons must appear on the product side, and the number of electrons lost must correspond to the increase in oxidation number of sulfur, which it does. For the reduction half reaction, I will show permanganate anions being reduced to manganese 2+. I will balance oxygen by putting 4 water molecules on the product side. Then I have to balance hydrogen by putting 8 hydrogen ions on the reactant side. And then to balance charge, I need to add 5 electrons. Once again, the electrons in the reduction half reaction must be on the reactant side because reduction is a gain of electrons, and the number of electrons gained must be equal to the decrease in oxidation number, which it is, from +7 to +2. Everything looks fine. So now, to add these together, I must have the electrons cancel. 2 electrons lost in the oxidation, 5 electrons gained in the reduction. The least common multiple of 2 and 5 is 10, so that means I need to multiply the oxidation half reaction by 5 and the reduction half reaction by 2. Once again, don't take any shortcuts. We're going to write these out. 5 sulfites plus 5 water molecules form 5 sulfates plus 10 hydrogen ions plus 10 electrons. And for my reduction half reaction, multiplying that by 2, I get 16 hydrogen ions plus 2 permanganates plus 10 electrons form 2 manganese 2 cations plus 8 water molecules. Now I can add them together. Let's see what cancels. Oh, electrons cancel electrons. I've got 10 hydrogen ions on the product side, 16 on the reactant side. These all go away, and this becomes a 6. I've got 5 water molecules on the reactant side, 8 on the product side. These all go away, and this becomes a 3. So now when I add these together, I get 5 sulfite anions react with 2 permanganate anions plus 6 hydrogen ions to form 5 sulfate anions plus 2 manganese 2 cations plus 3 water molecules. And once again, please take a second to pause the video and check to make sure that elements balance and charge balances, and in fact it does. Now, each of the 2 examples I just showed occurred under acidic conditions, meaning that there was excess hydrogen ions. That's what allowed us, in balancing each half reaction, to use as many hydrogen ions on the reactant or product side as we needed in order to balance. Okay? Well, what if the reaction occurs under basic conditions, which means there's excess hydroxide? Well, you may ask yourself, what difference does it make? Well, there are 2 answers to that question. Number 1, depending upon whether the conditions are acidic or basic, can alter the outcome of the reaction. Sometimes completely different reactions occur whether you're under acidic or basic conditions. So that's the important point. The second important point is that in order for the reaction to be accurate, if it's under basic conditions, you cannot have hydrogen ion in the final reaction because that would be chemically basically wrong. Okay? So what we're going to do, if it's under basic conditions, is to begin by balancing it using the method we just learned as though it were under acidic conditions. So we're going to temporarily pretend it's acidic and use hydrogen ion to balance hydrogen, just as we did. And then once you have your balanced but chemically inaccurate final equation, you will fix it by neutralizing any hydrogen ions that are present by adding hydroxide. And you will see what effect that has. So here's an example. Aluminum metal reacts with nitrite anions under basic conditions to form AlO2-, the aluminate anion, plus ammonia as a gas. Now, you can easily see that this must be under basic conditions because if this were under acidic conditions, the aluminate anion would form aluminum 3+ cations and ammonia would form ammonium ions. So we're going to begin as we did before by identifying who's oxidized and who's reduced. Aluminum 0, oxygen -2, nitrogen in nitrite must be +3, aluminum in aluminate is +3, hydrogen in ammonia +1, nitrogen -3. So we can see that aluminum is being oxidized. It's going from 0 to +3. So to balance that, aluminum goes to AlO2-. To balance oxygen, I'll put 2 water molecules on the reactant side. To balance hydrogen, I'll put 4 hydrogen ions on the product side. And to balance charge, I'll put 3 electrons. Again, a loss of 3 electrons in the oxidation is consistent with a 3-electron oxidation. For the reduction half reaction, I will show nitrite anions forming ammonia molecules. Nitrogen is balanced. To balance oxygen, I will put 2 water molecules on the product side. To balance hydrogen, I need 2 times 2 is 4 plus 3 is 7 hydrogen ions on the reactant side. And then to balance electrons, to balance charge, I need 6 electrons on the reactant side. That is consistent with a decrease in oxidation number of +3 to -3. Okay? Now, in order to get electrons to cancel, I realize that I only need to multiply the first equation by 2, so that I have 6 electrons being lost in my oxidation. I will again rewrite this. 2 aluminum plus 4 water molecules form 2 aluminate anions plus 8 hydrogen ions plus 6 electrons. I can simply add that to the reduction reaction before, which doesn't need any change. Let's see what cancels. 6 electrons cancel 6 electrons. Oh, the 7 hydrogen ions on the reactant side go away, leaving me with 1 hydrogen ion on the product side. The 2 water molecules on the product side go away, leaving me with 2 water molecules on the reactant side. So, to rewrite this, I have 2 aluminum plus 2 water molecules plus nitrite reacts to form 2 aluminate plus ammonia plus 1 hydrogen ion. Okay? Now, this is balanced. The elements are balanced, the charge is balanced, but it's chemically inaccurate because it has hydrogen ion on the product side, which would not exist under basic conditions. So here is how I fix it by neutralizing the hydrogen ion on the product side. What neutralizes H+? Well, of course, OH-. So I will add 1 hydroxide anion to the product side in order to neutralize the hydrogen ion, and this basically forms 1 water molecule. Now, to keep it balanced, I have to add a hydroxide on the reactant side as well. Okay? So now I'm under basic conditions, and the final thing I need to do to fix it is to recognize that I've got 2 water molecules on the reactant side, only 1 on the product side. So that means on the reactant side, one of these water molecules is going to go away, and that water molecule goes away as well. So now my final corrected equation to represent the fact that I'm under basic conditions, 2 aluminum anions react with a nitrite, 2 aluminum atoms react with a nitrite anion plus 1 hydroxide anion plus 1 water molecule to form 2 aluminate anions plus 1 ammonia molecule. And again, if you pause the video and check, you will see that atoms are balanced and charge is balanced, and the fact that hydroxide is a reactant and there is no H+, is consistent with the fact that this takes place under basic conditions. That's the half reaction method, and in our next video we will talk about voltaic cells.